Hello everyone. In this lecture we will discuss about the directed acyclic graphs. The directed acyclic graphs are the useful data structure for implementing the transformation of basic blocks of three address codes. So we have the three address codes. You should understand the sequence of how we have actually reached to the directed acyclic graphs. We have the three address codes. In the three address codes we can find out the basic blocks. The purpose of finding the basic block is to find out the loops in that based on the control flow analysis or the program flow graph. Fine. I again repeat what actually takes place, that we have the three address codes. All the three address codes will have the statements of assignments. We will have the expressions of arithmetic operations, then the array operations and the pointers, also some conditional jumps and the unconditional jumps. So every loop in the source code has now been converted to the conditional or unconditional jumps. Okay, now we do not have any loop in the three address code. To find out the loops in the three address codes, we will have to do the control flow analysis on the basic block. Okay, so we will have to do the control flow analysis. We will have to find out the basic block, then we will have to find out the program flow graph, and after program flow graph we will go for the control flow analysis on that program flow graph. That will give us the loops. If there is a cycle in that, we can say that there is a loop in the program flow graph. Now if we have the basic blocks of the three address codes, we have found the basic blocks of the three address codes, then we need to transform those three address code blocks to the assembly language codes. And the assembly language codes that we're going to write should have the minimum number of the temporaries. So it is going to play a vital role while generation of the code through the code generation phase. So let us discuss the directed acyclic graphs and its properties. So the directed acyclic graph is the first property of the directed acyclic graph is that it is a kind of the tree which will have no cycle. Obviously, the name suggests that it is a directed acyclic graph. It means this is the kind of the graph wherein there will be no cycle. In this, there will be leaves, and there are different levels in the acyclic graph. So the leaf nodes here in the directed acyclic graph will have either the identifiers or it will be a constant. So leaf nodes will either be the identifiers or it will be a constant. In this graph, there will be some internal nodes also. Leaf node means there will be no further extension after the leaf node, but the internal nodes will have some extensions. So what will be the internal nodes? Internal nodes will be the operators. Fine. So the internal nodes will be signifying as the operators. And every node which is there in the directed acyclic graph, they are given a sequence of identifier for some label. Okay, so nodes are also given a sequence of identifiers for label. Sequence of identifiers for label. Okay, so you should not worry about if the third point is not clear to you, because we will be taking the example to make you clear all these 3 points. But there is one more property of this directed acyclic graph, that there will be exactly one DAG for each block. Okay, we have already identified the block of the three address codes, and you can see my earlier lectures of the code optimization wherein we have discussed about the basic blocks. So every basic block is defined by one DAG or one directed acyclic graph. So let us take a very simple example and try to understand this basic block. Suppose we have a basic block A equals to B plus C, then B equals to B minus D, then C equals to C plus D, then E equals to B plus C. And we have to form the directed acyclic graph for this statement. So this actually is representing one basic block. One basic block is having 4 statements. Let's say we have named it as the B1 basic block. And we now have to find the directed acyclic graph corresponding to this. So for finding the directed acyclic graph, let's take the first expression. In A equals to B plus C, B and C will be the identifier and the plus operation is performed on them. Just as we used to construct the syntax tree or the expression tree, similar way we are defining that B plus C operation has been performed and the B plus C operation's result is saved in some A variable. So we have assigned the label A on this node. So this is the third point here. Nodes are given a sequence of identifiers for label. Okay, so A name has been assigned to this particular node. Now after this the operation is B minus D. So for performing B minus D operation, you will not have to define this B, or you will not have to create this P node again. Once it has been created, we will be using the reference of this only. So we are not going to create another node for this. So this is B minus and D operation because D has not been made earlier. So we will be making a new node for D. So B minus D operation has been performed and the operation result is saved in B only. Now see, a B was already there and the result is also saved in B. Fine. Mathematically it's not correct, but with respect to the computer science it is correct, because in the computer science it is allowed that the result can be saved in the same variable. Fine. Now to distinguish between this B and this B, let us name this B as B0. Okay. Now after this we have C equals to C plus D. So C plus D operation is performed. So plus is the operation which is performed with C and D and the result is saved in C. Now again to differentiate between this C and this C, let's name this C as C0. Fine. Now after this the operation which is performed is B plus C. So here we have B and here we have C. So either you can perform with this B and this C, but this B and this C has been produced later. So we'll be using the later references of B and C, and then this B and C are added and the answer is E here. Okay, this is very interesting to understand that once we have found the new reference of B and C, we will be using the new reference of B and C in the further operations. So this is the DAG for this basic block. Let us take another example. It is A equals to B plus C, then B equals to A minus D, C equals to B plus C, and D equals to A minus D. So let us draw the directed acyclic graph for this. So for the first statement, this again I tell you that these are the statements which are there in some basic block. Let's say this basic block is B2. So we have B plus C operation performed and the result of the B plus C is saved in variable A. So operation is plus. So operation is specified inside the node and the name of this variable is A. Fine. Now after this A minus D is performed. So we will be taking the reference of A from here and the minus operation is performed with D. So A minus D is performed and the result is saved in some P variable. Now once again, just to differentiate between this B and this B, we are writing here B0. The next one is B plus C. To perform the addition operation on this B plus C, you just see that B plus C value has already been computed here. So since B plus C value has already been created, we should not create it again. we should just name that wherever B plus C operation is performed, here it was A earlier and C is there also at this place. Fine. So A plus C. So next operation is D equals to A minus D. We can find A from here. Okay. And then the D is here. So A minus D A minus D. A is here and D is here. A minus D is D. So we can say that D is here. Okay. So this is the directed acyclic graph for this basic law. So if you see this once again, that what has actually happened, first we have performed B plus C. So B and C were added and the result was stored in A. So this level is A. The next operation is A minus D. So A is here, minus operation is here, and D we are taking as a new one. So A minus D is performed and the result is saved in B. Next operation is C equals to B plus C. Okay, so B is here and C is here. The B plus C has already been computed, which is stored in A. B plus C again gets computed and that is stored in C. So we do not need to draw this again for the directed acyclic graph. This will be taken from here only, and A was the name of A plus B plus C. So C has already been given name for B plus C. So we just have to write A comma C here. Next operation is D equals to A minus D. You just see that A minus D has already been computed. A minus D. This is A minus D has already been computed, which had a value B. But we can assign D also to this place. Okay. Now just to differentiate this D and this D, you can apply a D0 here. Okay. So this is the basic block for this one. Now we can take one more example of this basic block. Let's say this is X equals to AI. And then AJ is equals to Y. And then Z equals to A of I. Now it is very interesting that we have the array operations. So for array operations, this angle brackets are saved in the angle brackets are kept in the nodes, internal nodes. Okay. So the first thing is X equals to AI. So A and I will be the value of the nodes A and I as a leaf node, and these are representing the array A angle bracket I. So this is referencing AI. The value of AI is stored in X. So this level is X. Okay. Now this X is equal to this one. So this node is containing equals to followed by the angle brackets. So AI value is assigned to X. So X equals to AI. Okay. Now next operation is AJ equals to Y. So A is here. Let's take a J, the new one, and AJ is assigned to Y is assigned to AJ. Okay, Y is assigned to AJ. So we need to have one more variable or one more node to this, that is Y, and then this is AJ is equals to Y. Okay, AJ is equals to Y. Achha. Then here also in the node we are writing like this, angle bracket followed by the equals to sign. Okay, so the angle bracket followed by the equals to sign is being assigned to Y. So AJ is equals to Y. Next reference is Z equals to AI. So AI has already been computed. Okay, AI has already been computed, so you do not need to compute it again. So value of AI is stored in J. So you just need to assign a Z here, or you just need to name it as Z. Okay. So this is the directed acyclic graph for array statements. Let us take some more example, and this will be a bigger example, or the question which will have many statements, and then we will see the optimization also with respect to the directed acyclic graphs. Let's say we have the statements. We have the intermediate code generation statement as a 3 address code. T1 is equals to 4 multiplied with I. Second statement is T2 equals to A T1. Then T3 equals to 4 multiplied with I. T4 is equals to B T3. T5 is equals to T2 multiplied with T4. There is no restriction on the number of the temporary variables. You can take any number. For one basic block, these statements are given: product plus T5, and then product is equals to T6, T7 is equals to I plus 1, and then I equals to T7. Then we have a conditional jump. If I is less than or equal to 20, then go to 1. Let us name these statements. Label this statement 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. These are the labels of the statements. Let's draw the basic block for this. Let's draw the directed acyclic graph for this. All these statements are coming in one block. That I have already told you that there will be exactly one directed acyclic graph for one basic block. So the first thing that we have is 4 multiplied with I. So multiplication is the operation with the operands 4 and I, and the name given to this is T1. After this, we have to perform A of T1 and we have to store that in T2. Okay, so we have the array reference operation which will refer to T1. So A under angle bracket T1, and this value is assigned to T2. So T2 is the level of this node. After this, we have to do for T3 equals to 4 multiplied with I. You just see that 4 multiplied with I has already been computed. We just need to assign this a name T3. So 4 multiplied with I has already been computed. We just need to assign a name T3. After this, we have to do B T3, and this value has to be stored in T4. So B T3 will be referring to this in the angle bracket, the T3, and a value B, which is a new value for me. So B T3 value is assigned to some temporary variable T4. Okay, so I again repeat that inside the node, inside the internal node, we either are writing like this if we have some variable x on the left side which is assigned a value of the array value, and if we have to assign something in the array value, it is written like this. Okay, now so B T3 value has been assigned to T4. So fourth statement is done. After this, we have T2 multiplied with T4. So where is T2 and where is T4? T4 is here and T3 is here. So we are going to perform the multiplication of this T4 and this T2, and the answer is stored in T5. Okay, now next operation is T6 equals to product plus T5. So we have to perform the addition. Product is the new variable which is coming up, so a new node will be created for this. So product plus T5, this value will be stored in T6. After this, we have to assign the value of this product to T6. It means this product plus T5 value has to be assigned to product because this is T6. Or you can say that by this statement, product is equals to T6. Product is same as that of T6. Now earlier I told you that if we have to differentiate between this one and this one, you just name this variable as product 0. After this, we have the statement T7 equals to I plus 1. So I is here, apply an operation plus, and 1 on the right hand side, assign this a value T7. Fine. After this, I equals to T7. So I is given the name to this label. Just to differentiate this one and this one, you can write it here as I0. After this, we have a conditional jump. If I is less than or equal to 20, go to 1. Fine. So less than or equal to is the operation, relational operator which is performed on I and 20. So I is on the left hand side and 20 is on the right hand side. We are assigning this a value, and we have to go to label 1 here. So to assign it a label, we will be writing it like under the parenthesis, we are going to write the label number which is 1 here. Okay, I again repeat with the last statement how we are writing the conditional jump. If I is less than or equal to 20, so we do not have to write here I. It is just that we have to apply the relational operator. On the left hand side there is I, on the right hand side there is 20. So comparison is made between I and 20. If I is less than or equal to 20, we have to go to 1. So just to represent the conditional jump, we have to write 1 here. Okay, so this is the directed acyclic graph of the 3 address code statement which is given to us. Now having done this, we just need to find out what are the applications of the DAGs. Also already we have formed this, but what are the application of this DAG? So if we have formed the DAG, the very first application will be that we have to find out the common sub expression and eliminate the duplicates. Okay, so we have to find out the common sub expression. So very first application is find the common sub expression and eliminate it. Second is we have to find out which name is used here in this block, which name is used in this block, but what was evaluated outside this block. Okay, for example, here we are going to use this I, but this I was declared somewhere else, or I was actually given a value somewhere else. We are just using this I here. Similarly, the product has been computed somewhere else, but we are actually using it here. So the second application of this is we have to determine which value are used in the current block but was declared outside this block. In some other block, this value has been evaluated. We are just using those values. Similarly, another application of this would be that we have actually computed the value of something here, but the value of this is being used by somewhere else. So if we have to determine which statement of block could have been computed, in current block but being used outside the block or by some other block. Okay, so one of the variable which is assigned a value here but is being used by somewhere else. Okay, so these are the three applications of this. Now for the 3 address code that we have already written here, let us find out what are the labels or what are the statements here in which there are multiple labels assigned. So what is this one? T6 and product. Another one is this one, T3 and T1. Okay, another one is here, T7 and I. Okay, we just have to, according to the first application, we have to eliminate the duplicates. Okay, we have to eliminate the duplicate statements. So let us try to find out this. We have the different temporaries T1, T2, T3, T4, T5, T6 and T7. We have just written this in the sequence. Now let us write the first statement. First statement is T1 is equals to 4 multiplied with I. So this is a required statement. Second is T2 is equals to A T1. This is also a required one. Okay. The third statement says that T3 equals to 4 multiplied with I. So we already computed this 4 multiplied with I, which was assigned to T1. Okay. So now T3 has no requirement. So we can eliminate this T3, and similarly we can eliminate this statement also. So this statement is not required. So we're going to write the next statement then. So the next statement here becomes T4 is equals to B of, instead of writing T3, we will be writing T1 here because the T3 has been removed and T3 is same as that of the T1. The next statement is T5 is equals to T2 multiplied with T4. Okay, so this is also a new one, so we'll be keeping this statement. The next statement is product equals to, T6 equals to product plus T5. First write this statement. T6 is equals to product plus T5. Fine. The next statement says that product goes to T6. So product is same as that of the T6. So T6 is not required. So instead of writing this T6, we can write here directly as product. So we are actually eliminating this statement. Okay, so product and T6 are same. If we already have the product with us, so no need of creating the temporary variable T6. So T6 is not required here. We have eliminated this statement also. Now after this, we have the statement T7 equals to I plus 1. So T7 is equals to I plus 1. The next statement says that I equals to T7. So I equals to T7 means we already had this I. Why did we create this T7 as a new temporary? So this new temporary is also not required. So instead of writing this T7 here, we are writing I equals to I plus 1. Fine. The next statement here is if I is less than or equal to 20, go to 1. Fine. So this statement will be as such because this is a new one. So if I is less than or equal to 20, go to 1. Fine. So see that we, instead of writing the 10 statements, we have reduced it to 7. So we have done some kind of the optimization here. So new temporaries which were created unnecessarily have been deleted, and we are now with the optimized code. So directed acyclic graphs are going to play a vital role in the code optimization as well as in the code generation. Fine. So we have found that these are we have found that we have the common sub expression and we have eliminated it. So this is the first application which is clear. Now the second application says that we have to find out the value which is used in the current block but was declared outside the block. Okay. So you can just see that which is the variable we have started using it directly. So I is a variable which was started being used directly. Similarly, product is the variable which is started being used directly. No other variable. So this product and I are actually being depicted in this application number 2. We are using its value, but we have not initialized its value here. Fine. Now determine which statement of the block could have been computed in the current block but being used outside this block. This is the third application. So where we have computed the value in this statement, yes, we have used the value, we have computed the value of this product, but we have not used product A anywhere else. We have not performed any operation with the product here. We have not performed any conditions, any conditional aspect of the product is not there in this in these statements or in this block. So product is the value which is computed here but will be used outside this. But what for I? We have computed this new value of the I, but the I value is being used here as a condition. So the third application is not for this I, this is only for this product. Okay, we are computing the value of product here, but this value will be used by some other block. Fine. So this is something about this directed acyclic graph. You can take many other examples and you can form the DAG by yourself. Thank you.